Chapter 6 next, counting. It sounds easy, but yeah, it's not so easy, we'll see. And then this first section we look at the basics of counting. So for simple problems, so if you're trying to count the number of different ways something can happen, you could just try to list all the ways. So that won't be possible with more complicated problems, or if there are big numbers involved. But example 1 is simple. So in this question, how many ways can you get dressed if you're choosing between, say, 3 shirts? A, B, and C are the shirts, and 2 pairs of pants, P and Q. Well, the first way to get dressed is shirt A and pants P. Or you could try those shirts B or C with P. And then there are also 3 options if you wear the pants Q. Alright, so 6 options, 6 ways to get dressed using 3 shirts and 2 pairs of pants. So that makes sense, and we can make a list of all the ways. And we've seen things like that before. But it illustrates an important principle. We can call it the product rule. So if we have a procedure that requires 2 tasks, 2 jobs, if the first task can be done in X ways and the second can always be done in Y ways, then there are X times Y ways to do the procedure. So here the first task was picking a shirt, 3 ways to do that. The second task, deciding which pants to wear, 2 ways. So altogether 3 times 2 is 6 ways. For example 1, depending which shirt you picked, that didn't change your pants options, but it could for more complicated problems. But all we need is that whatever happens in the first task, the number of ways to do the second task is always the same. Alright, so always Y ways to do the second task. It's possible they could be different ways depending on what happened in the first task. And if there was a third task that could be done in Z ways, then you just keep multiplying, and so then X, Y, Z ways to do the procedure, and so on. For more tasks, you just keep multiplying, so you get a bigger product. Example 2, you see an online product, some online merchandise that comes in 6 colors and 7 sizes. So how many possibilities is that? So what, if you're going to buy this piece of merchandise, how many options do you have? Well, yes, it's just two tasks here. So the first task is picking the color, 6 ways. The second task is choosing the size, so 7 ways. So by the product rule, there are 42 possibilities. And you could list them, you could make a table, but there'd be 42. You'd see all the 42 options. Example 3. This looks different. So S is this set. The numbers, the integers 1 through 6. T is the set of integers 3 through 9. And the question is find the cardinality of the Cartesian product, S cross T. Okay, so remember when we started working on sets, we looked at this Cartesian product idea. So the Cartesian product, it's a new set. It's a set of ordered pairs, A comma B, such that A comes from the first set and B comes from the second set. And of course, cardinality just means how many elements are in this this new set. Okay, well, we're choosing. So the first, the A is coming from the set S. Our first task is to choose A. And then the second task is to choose the second element. So coming from the second set, you can see T has, in fact, 7 elements. And so 7 choices. All right, so so the first, if you choose 1 from S and 3 from T, you get this ordered pair. Or 2 from S and 3 from T, you get this guy. All right, you see all the options. Yeah, there are going to be 42 possibilities again. The last option would be 6, 9. Okay, so again, it's the product rule. And this example 3 is really the same as example 2. S could be the set of colors, T could be the set of sizes, so it's really the same question. Okay, so these examples are the next examples, just illustrating this product rule. So again, if a procedure requires 2 tasks, and you can do the first task in X ways, and the second task in Y ways, then altogether there are X, Y ways to do the procedure, so you multiply. Example 1 in the book. A new company with just 2 employees, Sanchez and Patel, rents a floor of a building with 12 offices. How many ways are there to assign different offices to these 2 employees? All right, so think of it in terms of tasks. So the first task, we want to give Sanchez an office. And there are 12 ways to do that. There are 12 possibilities. Second task, Patel gets an office. Okay, so he can't have Sanchez's office, but there are 11 options left. So by the product rule, the answer is just 12 times 11. That's 132 ways. So you could imagine making a list of the possibilities. But it would be a big list. So better to just use the product rule. Okay, so I hope you're getting the idea. Example 2, the chairs of an auditorium are to be labeled with an uppercase English letter followed by a positive integer not exceeding 100. Okay, so an uppercase English letter, so there's 26 of those, followed by one of these numbers. Okay, so positive, that means starting in 1, so there are 100 options for the integer. What are the largest number of chairs that can be labeled differently? So first task, choose the letter. Second task, choose the number. And by the product rule, that's 2,600 different possibilities. And example 3 is similar, so 32 of these microcomputers, each with 24 ports. How many different ports are there altogether? So just the product. All right, so what's the moral? So we always multiply any two numbers we're given in a counting problem. Let's see. Example 4. Suppose a multiple choice test has 5 questions, each with 4 possible answers. Suppose a student is just randomly choosing answers. How many ways can this be done? Okay, so how many ways can you randomly fill in the answers to a 5-question multiple choice test like this? Can we just use the product rule? 20 ways? Nope. So it's a good idea to think about the tasks. So what are the steps here? Well, the first task is to answer the first question. How many ways to do that if you don't know the answer? Well, it's multiple choice with 4 possible answers, so there are 4 ways. Question number 2, that's the second task. There are 4 ways to do that. And in fact, so 5 questions, so it's really 5 tasks. So it's X, Y, Z, W, t, so we're multiplying 5 numbers together. Yeah, so it's 4 times 4 times 4 times 4 times 4, so 4 to the power of 5 is 1024. Yeah, so you can see certainly a lot more than 20 ways to answer the quiz, answer the test. Yeah, that's why these multiple choice quizzes can be difficult. Yeah, if you're not quite sure of the answers, yeah, there's lots of ways to go wrong. Only one way is everything correct. All right, so the moral in example 4 is, yeah, these counting questions can be tricky, so make sure you think through your answer. You can't just apply the product rule to any two numbers. And yeah, try to think about what if you were trying to list all the answers, what would that look like? That's helpful. Next example, counting bit strings. So how many bit strings are there of length 6? Okay, so remember our bit strings, they're just zeros and ones. So a bit string of length 6 might look like this. So this is a random example, but yeah, so when I was coming up with this example, the first task was to choose the first digit, the first bit. I had 2 options, and then 2 for the second, 2. All right, so this is similar to this one. You're, instead of choosing one of 4 answers, now you're choosing one of 2 possible bits. So the answer is 2 to the power of 6, 64. So 64 possible bit strings of length 6. All right, so yeah, so this time 6 tasks. Example 6, let S be the set of these 6 numbers, -1, 0, 1, 2, 3, 4. How many subsets does S have? Okay, so how many smaller sets are contained in S? Smaller, or including S itself. So yeah, this is the product rule again. So what are the tasks? Well, the first task, the first job is to decide, do we want to include this first element in our subset? Okay, so yes, we include it, or no, we don't include it. So 2 options. Do we include 0 in our subset? So that's another 2 options. All right, so for each of these 6, we have two choices. So again, it's 2 to the power of 6. So the answer is, yeah, there are 64 possible subsets of this set, S. Okay, so yeah, it's another counting problem. for each of these 6 steps, we're deciding, do we want to include an element or not? And again, yeah, these 2 examples are really the same. Yeah, remember we saw it when we looked at sets in section 2.2 that subsets correspond to bit strings. So instead of using yes or no, we could use 1 and 0. So the subset that includes all the elements, that's, we're listing them in this order, that's all 1s. If we don't include 4, then we'll make that last guy a 0. If we just want to include the first, the third, and the fourth, then we'll have 1, 0, 1, 1, 0, 0. So this bit string corresponds to this subset. And this question, this was in one of the homework questions. So if you don't include any of the elements, so a string of zeros, then that's the empty set. So in these last 2 examples, we've seen both of these lists contain 64 elements. All right, and some more in the book. Example 5, how many different license plates can be made if each plate contains a sequence of 3 uppercase English letters followed by 3 digits, not excluding any possibilities. So now we're multiplying it. The 26 options for the first letter times 26 times 26, that's the letters. And then the digits 0 through 9, there are 10 of those, times 10 times 10. So 6 tasks. And these are the number of ways to do each task, and they all get multiplied. So lots of possible license plates. Example 6, counting functions. How many functions are there from a set with m elements to a set with n elements? So, so what are we choosing? So in the domain, we have m elements. And if we're making a function, we just have to decide where to send each of these into the codomain. So pick the first element in the domain. Well, there are n options, different places to send it. Okay, so we get our first task is n ways to do it. Then take the second element in the domain. There are still n places to send it. There's no restriction on this function. Okay, and then so we just keep multiplying these n's. There are m. We're multiplying n by itself m times, so n to the power m is the answer. Example 7, yeah, it's more complicated. If you want the function to be one-to-one, so then, yeah, so you have to assume that the number of elements in the codomain is greater than or equal to the number of elements in the domain. Otherwise, it's not possible to have a one-to-one function. So choosing where the first element goes this time, yeah, it's still n ways. But for the second element, so now if you want the function to be one-to-one, you can't send it to where the first element went to, so now there are n-1 options, n-2 for the third. Okay, so you get this kind of a product. So this counts the number of one-to-one functions. Okay, so it's going to be less, it's more restrictive. How about this one, example 9? What is the value of k after the following pseudocode is run? n1, n2 up to nm are positive integers, and we have this these nested for loops. So k starts out at 0. The outer loop I sub 1 goes from 1 to n sub 1. Then inside that, I2 is going from 1 to n sub 2. Yeah, there are m of these loops. So yeah, in the first case, all these i's are equal to 1, and on the inside, I sub m goes from 1 to nm. Okay, then k increases to nm. But then that gets repeated n sub m-1 times. Yeah, so this loop, these loops, yeah, k increases a lot. In fact, when these have all finished, it's going to be the product of the sizes of these loops. Yeah, so that's kind of an awkward example, yeah, but bringing in some coding. All right, let's see what else can happen. Example 7. Suppose you have room for one more class in your schedule for next semester. You see 4 possible math classes and 3 possible computer science classes. How many options do you have? All right, so you have room for one more class, 4 possible math classes, 3 possible computer science classes. So do you have 12 options? No, you only have 7. So in this case, yeah, there's only one task. You're only choosing one class, but there are 4 options here, 3 options here. So you're just adding in this case. You can make a list. Yeah, your list would just have 7 possible classes. So So yeah, the answer is 7 here. So yeah, we just needed a different operation, just addition. And that's an example of the sum rule. So if a task can be done in X ways or Y other ways, all these ways are different, then there are X plus Y ways to do the task. All right, so the difference here is, yeah, there's only one task. Yeah, it would be a different question, yeah, if you were choosing 2 classes, 1 math, 1 computer science, and there are 4 and 3 options, then it would be 12 for choosing 2 classes. But here, yeah, it's just making one choice, and it's 3 plus 4. And that generalizes to X plus Y plus Z if there are Z other options. Or yeah, you might need more letters. Example 8, you're looking to buy a new car, and you narrow your search to 4 possible Fords, 3 makes a Toyota, or 5 Hondas. So how many ways can you buy a new car out of these options? So again, yeah, we're just adding. We're only buying 1 car, so it's going to be 4 plus 3 plus 5. Yeah, it's just we just need to sum the options. So yeah, 12 ways. Okay, yeah, so now it's getting confusing, these different kinds of options. Example 12, suppose that either a member of the mathematics faculty or a student who is a mathematics major is chosen as a representative of a university committee. How many different choices are there for this representative if there are 37 members of the math faculty and 83 math majors, and no overlap between those two? Yeah, so that's just the sum rule. We just need to add those two. We're only making one choice. There's only one task. So 37 plus 83 is 120 ways to pick the representative. Again, yeah, if you're picking 2 representatives, one from the faculty, one from the students, then it would be the product. So a lot more options, but we're only making one choice here. One more example. A student can choose a computer science project from one of these 3 lists. So the 3 lists contain 23, 15, and 19 possible projects, respectively, so on each list. There's no overlap in the projects, so how many possible projects are there to choose from? Again, yeah, I'm sure you can see it's just the sum of those numbers. All right, So that's the sum rule. And we can summarize yet just using our set notation. So the product rule, as we saw in our example, the cardinality, the number of elements in the Cartesian product of two sets, A cross B, is just the number of elements in A times the number of elements in B. Alright, so if you're choosing an element in the Cartesian product, it's an ordered pair, choose the first guy in A, the cardinality of capital A ways, the second in cardinality of capital B ways, so it's a product. For the sum rule, yeah, that's more like the cardinality of a union of two sets. So if you have two sets A and B with no elements in common, so they have to have no empty intersection, then the number of elements in A union B is just the number of elements in A plus the number of elements in B. And yeah, we'll see next what happens if they do have elements in common. Okay, so that's the sum rule and the product rule, so these basic counting techniques.